But yeah, you'll have to do a final. Are you okay with the Zoom? Are you okay with the Zoom? Hello? Recorded? See the recording? Okay, thank you. Okay, so let's continue with CNNs. So today we'll look about training. Here I am. So we'll look at basically what are the different challenges, and it will feel a little bit like almost like revisiting calculus, more or less. And then we look at the different algorithms in PyTorch, where you do really your backpropagation optimization. And then we'll just mention if you want to do a second order. So a lot of what you will see today, you have seen before, so it will be a good revision. So this is basically kind of a timeline of the different architecture that we have looked at. We focused on AlexNet, VGG, and ResNet primarily in this course. But for the project, I received quite a bit of questions asking on Tuesday, are we limited to these in your project? I mean, your project is your project. I mean, do whatever you want. Right? Use anything that you would like to use for the project. Yes, don't reinvent the wheel. There is a code out there in GitHub, just use it. So basically, PyTorch libraries, whatever. Yes. So it is a project, right? So you don't have to limit yourself to these architectures if you choose something else. Okay, training. So let's look at this. Let's see, I think I have, yeah, this is. Okay, just let's remember what we are already doing. We have the CNN, we're still doing the MLP. You go from the left-hand side, which is your data, you feed forward until you get to the output, basically, the final layer. And then now you have basically this is the classification problems. You have your logic, you have your final classes. And then now you have a hot vector, you look at the difference, and then you backpropagate, right? While you are backpropagating, remember that basically nested function, that for derivatives that we did in MLP. Basically, that's what we are trying. You are trying to minimize. You are trying to change. When you first initialization, you are feed forwarding. You just made the initialization of the weights. You just guess the weights, right? So you have a seed. You have randomized basically the weights. Now, when you are backpropagating, you are trying to change these weights. How much I need to change them so I can really lower my loss function, whatever that loss function is. So basically, that's basically where the gradient descent or the stochastic gradient descent come into the picture, right? So now, definitely, we have all kinds of different problems. Local minima is just basically the beginning. And here is basically an example of where you could really have local minima. But the overall plan is the same what we have done before. Is nothing really has changed whatsoever. So you're already updating your weights by basically looking at the gradients as well as you have a learning rate. So you have to set up this hyperparameter, the learning rate, and you are hoping basically that you are really kind of converging over time to the global minima. Definitely, the learning rate will give you basically how much you are really converging. I will see some examples today. So if you do it really too much, then you already start to bouncing around, right? If you do it very small, then basically you are really converging very, very slowly. It will take forever basically to train, right? But now there is a compromise. Maybe there is a local minima. If the learning rate is high enough, it will jump over the local minima, and that's a good thing, right? So now you start to see basically it's not really a straightforward decision to say, okay, I will always have it low or I will always have it high, because it could really help you to escape a local minima, right? So that's basically one of the good things about choosing the learning rate. So basically, again, we did this. How do you update? Do you consider the entire data set? Do you do a single sample, or do you do a mini batch? Each one of those basically is considered. I've seen those before, those curves in here. So this is really the batch gradient descent, where you are looking at basically the entire data set. You're looking at the entire data set in here, and then updating basically the gradients and the weights based on your calculations of the gradients for the entire data set at every single iteration. And that's why basically you really get a very smooth path as you convert to the global minima in this case. You could replace that and start to say, okay, I want to do a mini batch because it's taking too much time to do this whole thing for the entire data set. So now I try to split my data into subsets and some batches. And then for every, I take one of these mini batches. I do my calculations, and then I start to basically converge every time I do a new mini batch. So I recalculate basically. So I have a first mini batch, I update, I move the representation space. I'm here, and then I do have another mini batch. I move here, another mini batch. So you can see basically not all, because of the randomness element in these mini batches, there's difference in the input data. You start to kind of not necessarily all the time you are moving toward the global minima, right? You start to kind of diverge a little bit in here. So, but nevertheless, this is really faster than what we had in the batch gradient descent. Okay, and then yes. Oh no, because it's sequential, right? Why does it say that performance goes to parallel over? You could do that as well, but usually it's sequential. It's just sequential. There is some data, for example, some images you want to keep overlap between them. You can really have two processes, and then you can have different mini batches. Then you can do them basically at once, but you are updating across them. So you update here, you go there, and so on. A zigzag. It's sequential. Yes, it's sequential. It has to be sequential, but you can, since you have many batches, then you can start to have some tricks how you can really use parallel processing in the training. And I'm not, we tried a few things, but so there are some other groups who have very innovative stuff from the computer architecture side of things. How you do that much more effectively. But yeah, it's still sequential. The same thing in here, right? This one here is basically you're doing every single sample every time, right? And now, because you are really picking a sample at random, you can see it's not really very smooth. And we have seen that in the MLP as well. So it's really going around. You converge eventually, but the challenge with this one is that your chances of hitting a local minima is higher, right? Because you may hit a local minima and just get stuck there or a saddle point. Yes. Exactly. Well, yes, exactly. When the mini batch size is 1. Yes, absolutely. Yes. It's faster if things really work out very well, but the chances it works out not that high. Exactly. So in some cases it may help that you are jumping over or escaping a local minima, but the chances it will really get stuck on a local minima is higher than just escaping one. Okay, so this is the mini batch. I think we did this in a homework. Okay, so local minima is 1. The saddle point, if you remember this from your calculus days, if you look at this here, the saddle point, let's just look like a saddle. You have 2 directions, you have 2 features, you are stuck in here. Basically, there are 2 things. If it's really flat, right, then the gradient will become what, a 0, right? Then the algorithm will just settle down. So okay, I'm here, but clearly you can really go lower in the loss function, right? You see that. But the other more problematic is that in this direction, if you move this way, the loss will be smaller. If you move this way, the loss will be higher, right? So basically, and you have these 2 cases in here. So that's basically a serious problem as well in this optimization techniques. Okay, and the saddle points really are very common in whenever you have high dimensional data, which what you are dealing with. Right? You have these kind of 50 features or 30 features or so. The saddle points are much more common than what we are hoping for. Yes. Yeah, there are. Yeah, I mean, there are all kinds of different techniques. Basically, how you can do this. So as you are constructing this hierarchical representation space, but I cannot really tell you. It depends on the data situation, the loss function, right? Which optimization technique you are using, if it will help or not. But yes, there are all that kind of different techniques. It's like kind of hierarchical way of creating the space. Okay, so there are techniques that we will study right now in a few minutes where you want to change basically your learning rate, right? So there's an adaptive way to do it, right? That's one way to do it from the samples point of view, but that is not guided, right? When you do it from the sample point of view, remember, when you are doing it from a stochastic, you are really looking at, you are creating a representation space based on the previous samples. And now you go to a mini patch, right? So now there might be quite a bit of different distribution between these data sets, between this small data, right? That's the problem. What you want to do, you want to always try to converge to the global minima as you are optimizing, and then have some technique to adapt your learning rate, adapt your gradients. So it depends on what you are looking at. So what you are talking about is more of the alpha will be adaptive, right? I'm changing my learning rate as I'm going now. It's not really, you can do it as a function of the samples, but that will become very chaotic, right? It may cause more problems than. And remember, when you have your data loaders and you're starting to run, changing basically that in the middle of it may disrupt quite a bit the optimization. But I'm not saying it's not a good idea. So here's one of the more kind of the easy adaptive ways of how to achieve that for the saddle point. So if you have a saddle point in here, and that's from the calculus days, if you remember, this is the local minima. This is saddle point where it's very flat, and then there's a local minima in here. So one way is, let's just think about, can we add more? Like you can imagine this from calculus days. Basically, this is like a ball, right? So can you give it really more momentum, right? Can you give it really a push in the gradients, where it will not really settle down here? It will not settle down here. It will push it out from the local minima or push it out from this flat region. So you give it basically, and one way to do that, I mean, you can think of it as, I just want to basically increase my alpha, right? My learning rate, right? If I do that, but that's actually also is you do it for alpha is a hyperparameter. You do it for a few of them, but if in cases you may skip the global minimum, right? If the learning rate is not really carefully chosen. So one way to do that is just basically to have define this as velocity. I mean, just imagining this is kind of a ball coming down the curve in here, and then what we had before, right? Remember what we had? We had a w at t+1 equal w at time t, and then minus we have our learning rate alpha, and then multiplied by basically our Jacobian, right? So our gradients at time t, right? That's what we had. Now we are bringing in this velocity function. We just call it the VOT or velocity function at time t. At time t+1, this is nothing but basically you look at how the velocity was or what the gradient was at the previous time, right? Plus what basically the gradient was at the previous one. So you have kind of a running average throughout the time, and now you are controlling all of that using this parameter in here. If beta is equal to a 0, then all what you have is just this classic gradient descent, right? If beta is equal to a 0, then what we have in here, this v at t+1 is nothing but basically what we have derivative of the loss function at with respect to the w's, which is the Jacobians, right? So that's basically what if so you pick B, basically it tells you how much you want to incorporate basically the previous Jacobians, right? So that's basically what this whole idea is, and there are different calculations of it. So if you start to expand it, right? So now v at t+1 is equal to beta times v of t. Now replace v of t with how the calculation will it be for t+1 minus 1. That will be beta times v at t-1 plus the Jacobian at t-1 plus what I have this term in here, right? So now you start to see basically where the running average is coming from, right? So now the beta times beta is beta square of v at t-1 plus beta of the gradient at t-1 plus the gradient at time t. All of these basically three terms will basically give you what the v of t+1, and then you add that to our update equation. So this will come here and multiplied by the learning rate, and then update our weights, right? So basically you can see in here, as you really increase the window in here, then v at t-1 will be a function of t-2, v at t-2, and so on, right? So it'll be beta cube, v t minus 2, and so on. As beta basically is less than 1, then basically you start kind of as an exponential running average, because the very far away ones, will account much less compared to just the ones before, right? You see that, right? Because the beta square, beta cube, and so on, because these betas basically are between 0 and 1. This is the value for it, okay? Usually it's a little bit closer to the 1, right? Because as you really make it smaller and smaller, then as if you are not really doing quite a bit of updates, right? So you usually have like 0.8, 0.9, or very close to those values. Yeah, don't look at the one on the bottom. This is the link I put in the course content page. Very nice visualization on GitHub. You can download it and just play with it. But there are different formation for it. So this is the one we just saw, where basically you look at v at t plus 1 equal to beta times v at t plus the gradient, and then that will be basically scaled by the learning rate. Or you could do it this way, basically, where the update will be, the update is w plus the v at t plus 1, and then you bring in the learning rate into the equation to calculate the velocity at t plus 1, right? Both of these will result in a similar behavior. And here is basically looking at this demonstration here, where magenta is the momentum, especially with this formulation, and the crayon is the gradient descent. And you can see basically we have two, in this kind of made-up space, you have a local minimum on the right-hand side, you have a global minimum on the left-hand side, and you can see basically it's very easy for the gradient descent, the classical one, just to be trapped at the local minima. But for adding basically kind of more running average from the previous, I would say like push, like, or the gradient values, they're really pushing more. So that it really pushed it past the local minimum, right? And that basically kind of made it really land on the in the global minima. Any question about this? Where are they starting and where? Yeah, I mean, this is just basically this visualization. I tried to figure out if you can change the code to make it start somewhere else. I don't think we can, but it's just to prove the concept basically for this case. Yes, if you do, that's why you run it for different initialization. Usually your neural networks make sense and then just average, because it's if where you start, it's very important, right? Yeah, as well. But if you have enough, if you give your gradients enough randomization, let's say, I mean, or shake them while you're doing the optimization, then the initialization may not make a big difference if you average over 3 or 4 of these seeds, right? And you'll practice that in I think homework 6 or 7 and your project if you're doing project. Okay, so yes, you're not, because your formulation there is this formulation, right? What we have is this formulation, right? So it got stuck in here. Now, if you have a criteria when to stop, right? It satisfied the criteria, then you are stuck there, right? So it doesn't matter how much time you pass, that it's stuck there, right? In the local minimum. Basically, it's very, very common, right? It's very, very common in that case. So, but in here, the other one, it has already enough to say we scaled the gradients more, so we have more power for this ball just to move past the local minimum. Right? Okay. So another big problem is this curvature and condition number. So if you look at this space, right, and you look at this projection, is an oval projection onto this 2-dimensional space, right? So now, in one dimension, you have high curvature. In the other one, you have low curvature. And we have seen that, right? I mean, you see a little bit of this. This may be a little bit uniform, but that's very common. You have in one dimension higher curvature than in the other dimension, right? And then what we have on the left-hand side in here, basically how you can really calculate those. And this really has to do with the eigenvalues of the Hessian matrix. But without spending much time on that, basically how you can characterize which one. But if you are really optimizing and you are really, then there will be a domination from one dimension over the other. So you made the gradient will take you into one direction, and that will slow down the convergence, or it may even take you to a local minimum, right? So, and that's really a very common problem in this optimization. So, given the local minima, given local minima, saddle points, and the curvature and the condition number, there are many different ways how you can do this adaptively, right? So we looked at the momentum, but the most common ones that you will see based on PyTorch and TensorFlow as well are these ones. So really AdaGrad, RMS prob, and Adam, right? And Adam is really the most used one, right? I mean, I think if you take any pre-trained model, most likely they used Adam or anything else. And we'll study those today. Okay, so the adaptive gradient one, or AdaGrad for short, we are looking at basically, we're adding, you can see just right away, if you look at the momentum, we are looking at what? We are adding the sum of the gradients, right? The momentum. This one, kind of, if you look at it as a second order, right? We are really adding the squared, so the gradient squared, right? So we're adding them. So now we're scaling the learning rate by basically the square root of the squares, the sum of the squares of the gradients. Let me repeat that. So we are scaling the learning rate by the square root of the sum of the squares of the gradients, right? So now what that basically, an epsilon here, just kind of not to divide by a zero, right? So now if you have a direction that's really like a very high curvature there, or even just to make it simpler, you have one direction that's much steeper than the other one, they basically want to control that. You don't really want to have one direction to overall take over compared to the entire space. So it's really a simple modification here, but it gives you some advantage. So here is another from the same visualization. Again, the gray one is the AdaGrad one, or the adaptive gradient. So now this is the global minimas for this space, and now you have this saddle point, but because of the curvature here, basically is steeper. So basically the classical gradient descent is really going this way in here and then going that way. If you use the sum of the squares of the gradients, then basically you are moving into this direction, because you have the sum of square here this way, the sum of square this way. So this is basically the combined one, is going into this diagonal direction, right? And that, for this particular case, of course, for demonstration purposes, is really getting you much faster. You can see basically this arrived here almost like with half the time, like, I mean, more or less. But it's much faster in here. Not only is the speed, but imagine basically if you really don't really have enough momentum in your gradients, and you get stuck on the saddle point, right? Then basically you are really way far from the optimal global minimum, right? So you'll be just stuck in here, right? That's a problem, right? So you can see basically adding the sum of the gradients is really kind of getting us, for this case at least, kind of a useful solution. So now we have, yes. So if you look at the question is about basically what are we adding to the gradient? If you're not in here, right? We take the gradient as it is, right? We scale it with the learning rate, and we just use it, right, to update our weights, right? So now, if this basically get to a saddle point where it's flat or a local minima, then the next time you have an iteration, it will not be updated, right? There's not really much of a gradient to do. So now, in order to get out from that flat region or from that local minima, right? And that's basically one way to do that, is basically adding this kind of formulation, which is kind of the momentum, the first moment, right? So we take the Jacobian, we add to it basically some kind of a weighted the previous Jacobian. We weight that, we add it to the current Jacobian, right? And then the previous one, like 2 times behind, we add it as a beta square. So we less weight for it and fewer weight and so on, right? So we have this kind of an exponential running average in this case. In this one, we are really looking at it as, so that will help in both the saddle point as the local minima, but also it will help when we have situations where we have curvature differences. Basically, one direction is very steep, the other direction is not that steep, right? So now if you just take the gradient as it is, then it will go to the very steep one but that may take you far from the global minimum. And that's basically what we are illustrating here. So in here, we're trying to kind of bring something in between. So basically we take the square, right, and the sum it. So we have the square and and we sum them all together, and we update our weights accordingly in here. And that's what's really happening in here, right? We're really giving a kind of I don't know, I used to race cars, so I look at it as car engines. So it's you give it more power, more horsepower. That's okay. So this is basically the undergrad example. Yes, sorry.
The direction of the gradient, and like what is the power on the right?
Yeah, we'll have some examples. I will open the demo at the end, and then we can just have some examples and we'll look at that. You don't basically I mean we are visualizing this because it's two-dimensional, but usually when you have high dimension, you don't visualize it, right? So that's what we are trying to kind of mathematically to make that happen. But you are trying, if it goes basically here, right? This one to this one, that will hit a local minimum, right? And basically you are, for this specific case, that you are stuck, right? It's how can you avoid that? But if you look at the curvature here, if you are starting here, back to what Ryan was talking about, basically we are starting here. Both of them are really, both of the gradients are really into this half. Is really directing or indicating and the direction into this way and this way. So you will not hit that one. If you start here, if you initialize here, you will hit the local minimum. Right? So that's why you will have different seeds. I think it's 3 to 5 seeds for initialization, and then average the performance. That's usually a very typical common practice because of this issue. Okay.
The starting point it will flow more faster compared to
Can you repeat that?
A ball is falling to a starting point.
Uh-huh. So the question is, if we add the gradient some momentum and at the saddle point it will move faster, right? I'm not saying it's faster, it will have more momentum to get out from the saddle point and to be stuck there, right? But faster or slower, it depends on the direction, right? Especially if you look at the path here, right? If you look at this one here, this one really went through the saddle point, but not necessarily basically that means it get out of it, that means faster, right? This one is at least 50% faster, right? This one here is almost half the time, right? So I don't want to say faster. It's basically it has enough. The gradients have enough, basically, kind of amplitude to them that will not really settle down at the saddle point. Right? If you have it, so if you look at the learning rate, right? If you change the learning rate, it's really kind of control more or less. So that's what we're really doing here. We're scaling the learning rate. If you choose your alpha to be really high, which you are skipping, then basically yes, you are moving much faster. You are skipping. Maybe you'll just skip the whole thing, right? But that also may give you big problem because you just keep bouncing, you never converge. Right? We had an example in the MLP where it was a U shape or parabolic, and then you just keep basically hitting the 2 points throughout. So it's not a good idea to do that.
Calculation followed by like some kind of linearization function indicating this. So rather than using this, we have standardization, then we probably will get more like well-defined contours the view space.
So what do you mean by standardization? Like the typical gradient descent, you mean?
Take x minus mu by sigma. So now if we assume that all the features have like good weights, in that case, all the weights will also kind of be in similar ranges. They won't be like one feature has.
I see. Okay. Yeah.
So in that case, won't that like solve this problem? We won't need that.
If you don't have that curvature problem, and then it's a very beautiful space, and the weights are kind of not uniform, but they are within the same scale, then this one not really needed.
All the features have like.
But we cannot assume that all the time.
Kind of like draw the weights which are kind of go to zero, so that you don't need those weights.
So regularization the one at least that we discussed in the course in MLP, They will slow you down for sure. They slow you down, but they don't really work all the time to get you out from local minimum or saddle points, right? They really control if there is a dominating, like the curvature one, like the dominating one, right? If it really shoots, one of them shoots quite a bit in their value, right, for the weights. But it will not really kick the algorithm out from a saddle point or a local minimum. So in that assumption, you are not really at a local minimum, right?
Kind of all the features which you don't need to take the weights corresponding to those features to zero rates. So in that case, those gradients will be redundant for us.
Yeah, I mean, in that case, if you look at it that way, maybe, but is that something you want to do, right? That's the question, right? Is that something you want to do? So if you're just for classification, you have enough, then maybe. But if you're doing something like outer distribution detection, or you're doing adversarial, like sample detection, or you're doing even segmentation, actually, you want to keep those because maybe some of those data are really represented by those features, right? So it's regularization. There's quite a bit of different thoughts about it. It will slow down, but it doesn't. It's not always in favor of regularization because of this problem. For a classification, maybe it will work. That's a very, very good point. Okay, so this is one method, and then the other one is root mean square propagation. So in here, if you compare this equation here, right? If you just make the beta equal to 1, so this is basically if you look at here, just remember this: we have g plus the square of the gradient, right? And here we have g plus the square of the gradient, but what we add? We added this scaling factor. So we add this beta, right? We have this beta now. So we have this kind of, kind of a mechanism, right? That will resolve basically the problem by really adding a decay process to it, right? So this basically will give you kind of a decay, not to have one of them really shoot over time. So it's more controlling how you really do the update. Everything else is the same in the updates. The only thing that's different from the sum of the squared in the adaptive gradient is basically this beta in here, right? So if you think about what this really means, that this is still between 0 and 1. This basically means I will add more weight to the recent g values and less to the one from previous moments. So how does this really differ from the momentum one? The momentum one, we didn't really have the square, right? The momentum one, we didn't really have the square. All what we had basically is this value here, right? Remember that? So we had just beta times this. We don't have the square of the gradients. The difference between that and the RMS prob is really nothing but the square of the gradients, right? So, but the purpose of these betas is still the same, right? Is really kind of to account for the recent gradients, not the old ones. This again, so we have the green one is the RMSTP, and then here you have a local minimum. So now, what really this showing in here, if you look in the upper right corner here, these gray squares, these are the sum of the gradient squares, right? If you look at the sum, if you look at the first iteration here, we have the green one, right? And we have the gradient descent one in here. So now, in this one here, we are not really using the beta, right? So that means the gradient becomes much bigger, to the point where we have basically so huge that you don't really move anymore, right? In the green one with the RMSTP, we have this decaying where we don't really allow the gradient to become that large. And you can see that from the squares around the green area, right? This is nothing but the square of the gradients, right? In both directions. It's always manageable. It's not really as big as the ones without having this beta factor, right? So, and if you look at the gray ball in here with this very, very large squares, or the large squares of the gradients, at some point, it just basically, it got stuck. It doesn't really move any further because of the magnitude of these gradients in here. It doesn't really converge. But compared to the green one, we have added this beta in here, and that actually is really added quite a bit of advantage. It will keep moving to the global minimum in this case. And that's basically kind of a big difference between the ADA grad and the adaptive grad and the root mean square problem. It's a very, very big difference. This one, you can look at it as I'm doing a regularization on the gradient scale, right? But I'm not really doing it at the weights. What you're talking about is doing it at the weights. And here, we are doing it at the gradient one. And at least from my experience, and it's at least the last 20 years, it's adding constraints more on the gradient side of things than the weights. Actually, it gives you quite a bit of more better solution eventually than the weights. Okay, any question about this one? Okay, yes. So the question is this is exactly what they're showing. So now the adaptive gradient is the one where we are adding the sum of the squared of the gradients, right? That's the gray ball, right? So now if you look at the sum of the gradients in each direction, it will become a square, right? So basically that's what we have. Now, because of the dimensionality or the amplitude of these gradients, that becomes very, very large. So we represent this visualization here as the sum of the gradients squared as these gray squares, right? They become so large, right? So now you don't really have an update, right? So the weight basically will not be updated. You are stuck, basically. You are not converging anywhere, right? So you're not moving anywhere. So now what this one is adding this beta one, right? So now it's adding a decaying factor. So because beta is less than 1, right? So now you don't really accumulate, because the problem with just sum of the square of the gradients, start from instant 0 all the way to instant 50 or 100. You are accumulating, right? And that becomes so huge. Basically, it's you are not really moving anymore. The RMS prob one is adding a decay. So basically, you don't just keep adding from the first instance. You just look at basically the previous 1 or 2 or 3 or 4. That's it. What really matters. So what that means, the square of the gradients becomes manageable as you move on, right? And that's basically how you look at these squares. You see that squares around here is much smaller in that case. Does that answer the question? Because of this problem in here, so I would say always RMS prob is better, right? The only thing that you have another parameter to worry about called beta, right? Just because of this, and you will see basically now we added the problem of the square. So if you look at the add a grad in here, right? It's a very good idea. We are looking at this sum of the square, right? So the way you think about it, the first momentum is adding the first moment, right? This one is adding the second moment, right? Right. So now this is a good thing, right? But it generated a problem. To solve it, we added this decaying factor, right? So this one is more manageable than the previous one. I cannot really think of a stage where the adaptive gradient will be better than this one here. The only way it could be, maybe it could be faster than this one, because you didn't really have to do that averaging on the beta. But I don't really stand behind that statement. There's a big bet maybe behind it. But now Adam, which is adaptive moment estimation, which is kind of the de facto now. That's just if you go to any GitHub repo, you will use Adam basically as the default one, as a de facto one. Why? Because we use both of them. We use the first moment and the second moment, right? So we have, this is the formulation for Adam. So we have beta 1 and beta 2. So the beta 1 is the decaying factor for the momentum case. So we have the velocity v of t plus 1, and then we have beta 1 times v plus 1 minus beta 1 times the Jacobian. And then we have the beta 2, which is the decaying for the squared of the gradients, right? So this is really the adaptive gradient RMS prob in this case, right? So basically the Adam is really kind of adding these two together into one. And then you use the G of t plus 1 as your factor to change the alpha or the learning rate. And then here you multiply it by the v, which is from the momentum in here. So you are adding the momentum here, you are adding the second moment or the adaptive gradient in here. Right? So they're really both of these words. So now you have these two parameters, beta 1, beta 2, and usually these ones are really still, it's between 0 and 1, but usually they're already at the at the point, if you already make things move quicker, keep it at the 0.9, maybe 0.8 at smallest, but 0.9, 0.99, 0.97. I'll see some examples where you've changed these in that 1,000th basically place value that will make a bit difference in the algorithms. I will not go through this in much more detail, but there are some stability issues basically at certain iteration. So people really adapt that by dividing by the 1 minus beta 1 and minus beta 2 at previous times. It's just a scaling factor, just to remove any bias that we have. Okay, if you look at this example, I think I can open that one. Hold on. Let's see if I can. Yeah. I don't know what's happening. Let me open it again. It's not the best in terms of yeah, it's not. Okay, I think we can live with this one. Okay, that's fine. Okay, so if you look at, I have an example I want to show. Yeah, let me show this. So now all 4 of them are running. Let me show the paths. Let me make it faster. So you can see all of them get stuck in here, right? So this is basically you have kind of a hill that really push things down here, and then you have the global minima down here, right? So you have a small hill before it in here, another bigger hill on the right-hand side as they go down the steep, down the hill here. So now if you change, see the values, it gives you a very funny, okay. When I change this add to 0.2, this one to 97, I think that's 990. It made it, right? Just by changing these parameters, beta 1, beta 2, you can just see how sensitive it is to these numbers. That's where this hyperparameters is quite a bit of, this is part of the babysitting I was talking about, like when you are training, right? And this is just an example of how tough it could be just to do that. You can just do this for some of the other examples, like if you look at the local minima, right? Same setup, and you can see even between the local minima and the global minima, only Adam really made it over there, right? Even with this simple one. You can see maybe we need to push this a little bit more, right? When I push this, I don't know if this is a good idea. I don't know. Let me try. Yeah, it made it even closer. Before it was here, then it made this one. So oh, still. Much faster. Make it slower. Well, that will take forever. It's following the right path. Oh yes, just is the power -4, right? It's very, very slow. Do you think it will make it? Yeah. Yes, sir.
Seems that
No, that's what basically is. That's why I mentioned Adam is the default one because it adds both the first moment and the second moment. You're already having, you are pushing it into certain direction. Not in either one of them. So you're giving a boost for both of these using the beta one as well as this direction with beta two, right? Now the challenge will be they'll be sitting to really kind of, what will be the beta one, beta two values, but they are really very close range, like between 0.89 and 0.997. That's at that range where your values will be. Otherwise, it will go all over the place. Like even for this one, the global minima, it really managed to do it much faster, but escaped it, right? I mean, I just want to do this. You see how it escaped it and came back to it. So it's because of these numbers that I chose in here, right? You could really get better performance by changing these numbers.
why also
Oh no, you basically you it's a hyperparameter. You initialize them. Yes, you initialize them. Yes. Yeah, you initialize them. Yes. Yeah, not learnable. Yes. Okay. At least in the by default. Yeah, let's see if I can do this. And I have. Oh, this will be crazy because it will take it all the way. Let's do this. Nevertheless, is much faster than RMS prop. Yeah, is much faster because the first moment is pushing it. Now, if you look at the first moment, basically is look at it again. It went there very quickly. See, so the first moment really went there very quickly. Right? See that one. But the second moment is very slow. Right? You can just look at this and then say, okay, now for this kind of case, basically the first moment is enough, right, to do that. All kind of different things. Very interesting visualization. There are some other visualization, but I thought this one is it gets the point. Any question about this? I know the message is use Adam. It feels a little bit strange, but it is what it is. Yes. You can look at it from here, right? This is the simpler one, right? This one here, right? So as you increase beta one, right? That means what? You are incorporating basically more and more from the previous ones, right? So basically, right? Is it that the case? No, actually less, right? Less and less from the previous ones. So the values, this one will be smaller and smaller, right? But basically the learning rate will be higher. If you look at the square root of that, right? So basically you are scaling that way, right? And the same thing for beta 2. Because remember, beta 2, if it's 0.99, right? Then you are accounting for this one, for this G basically at 0.99, but this one 0.01, right? If you make it 0.8, then you are accounting for this one as 0.2, so it's higher for the previous ones, right? Compared to the current one. You see that? Okay. So here's some just ready from this is on her YouTube channel. She added some special cases. And you cannot really regenerate that basically as it is. So this is something she did. You can see it here. All of them are stuck here. This one really made it very beautifully to the global minimum. And this is another one where the global minimum in here, but there is a little bit of a hill before it, right? And basically, it's very easy if you have very high momentum, then not only you come through the global minimum, but you can even get out of it, right? If you manage to get over the hill, right? So she created this demo. So you can see there is the hill here. You see, these ones could not really make it, right? This one is managed. And then actually, if you play with these ones a little bit, if you play with them more and more, what you will face basically is that you can, if you are not really careful with the beta 1, beta 2, and the learning, the alpha, you will not only go to the global minimum, but you will skip it to this other side of the hill, right? So, and that's a problem. Yes. RMS, prob, or Adam? What do you mean?
Like, would I ever want?
Oh, to replace Adam, you mean?
Which has a high value conjunction.
Yes, you have high curvature condition number, right? In that case, you will use,
Momentum is just high to extract.
yeah, you will not, you don't need the first moment in that case, but you want to have more to the second moment. Yeah, that would be the case. Yeah. And we saw that in the, I think this one, I think it was the global minimum one. No, the local, not this one. Oh, this one here. Still, you see that one basically? It went here much faster, right? You don't, because the first moment tried to push you much further away. So that could be one case. But the problem with this, you don't really know about all of this before you start doing it, right? So that's where the babysitting of the training is very important. And there are tons of tools. What's that? Yeah, but once you start with it, then it's fixed, right? Then you have to redo it again and then just look at what's happening. It's part of the application studies you do, right? Yeah. There are some people trying to incorporate, but it's really it's all about your observation. And then when you talk about visualization later on, that's another tool you will use, where in that tool basically you look at what's really happening to your space. And we will have something either next Monday or the Monday after spring break. We took at visualization tools for CNNs, because those are very nice to give you some idea of what's happening in the network. So finally, she really went overboard to create art. That's what the author of this visualization did. So I just want to put it again. So it's I put the link on Canvas if you want to use it. Anyway, okay. So now finally, I want to conclude with what we did before about this Newton's method. Yes. So if you remember the gradient descent, right? All what we discussed so far, still a gradient descent, right? All what we have done is just the formulation from the classical gradient descent, right? All what we did, what will be the scaling in here? How can we do the scaling, right? What kind of moments we can add, first or second moments, and so on. But nevertheless, this is the representation space, right? Or this is the actual space. And then we are at this point in here, we are really modeling the space to be this planar, right? So we are really approximating it to be this plane, right? That's basically exactly what we're doing with the Jacobian, right? And now we are really trying to say, we're going to move basically across this plane, right, to reduce the loss function. And we did that, like when we talked about MLP, that's not really the best way to do it. If you could really replace this green one with the blue one is taking the shape of the space at that point, then when you're really moving across that blue space, then you are really having a much better approximation of what's really happening in the space itself. That's where the second order or the Newton's methods come into the picture. So all of these things, this slide and this slide, we have done these when we're talking about the MLP, and that's basically where we brought into the Hessian matrix into the equation. So now we have this quadratic one, you have the Jacobian, and then we have the Hessian matrix showing up in here. Simpler versions, just to look at it, is really the second order, right? We have looked at the second derivatives to look at the Taylor series. So we are taking the first, in the Jacobian, we're taking the first two terms. In the Newton's method, we're looking at the first three terms from the Taylor series expansion. So that's the Newton's method. So in PyTorch library and TensorFlow, basically there are 3 libraries. All of this basically we have done that before. Of course, there's a computation expense to it, but these are really the 2 methods that are there in the libraries, and we'll not use them in our homework, but you are free to use them for your projects if you choose to, or your homework 7, which will be a more open-ended homework. So this is basically the BFGS method, and then the LBFGS. So basically, this kind of has a limited memory. Is a version of this one that really approximate the Newton's method with less parameters and less disk space than the Hessian matrix in here. These are really they exist in there, but in summary, we really kind of Adam is really kind of the good choice. Basically, almost everybody use Adam. Almost everybody. I mean, all of those who really do work on optimization or interpretation or explainability of AI, then we can go to this one to see what's happening to the representation space. So if you look at CLR, papers, we see quite a bit of work in the Newton's method in here. But you pay the price because the Hessian matrix, right? Is much more complex to deal with than the Jacobian. Any questions? Just really kind of package optimization using CNN packages, more or less. I know we didn't really go into details too much, but I think it's enough just to make you aware of what's involved. Yes, Cooper. That's a good question. So now, will Adam be more effective when you look at the mini batches? Is that what you are talking about? So the mini batches and the whole batch, it's all about how much you can afford to do optimization at every single step, right? Now, how the Adam will change if you do from mini batch or a stochastic batch, it depends on the distribution of the data, right? So if the distribution of the data, if it's jumping all around, like every single time, then you will have this not very smooth, basically, even with the Adam will not be able to handle that very well, right? If the distribution of the data is keep jumping around. More or less, yes, more or less, yes. Not exactly, but yes. It's if you take things overall, yes, I would say yes. Would be closer. But also it's about how you calculate your beta 1 and beta 2, right? Because those will have a big impact on that, right? But if you keep them same, then I would say that statement maybe is very accurate. Makes sense. Yeah. Unless I missed something, but I think so, yeah. Any questions? Yes. Today. Yes. Yes. Oh no, Monday. No, Monday will not be part of this exam. Yeah, until today. So from lecture 1 to lecture, yeah, to today. Yes. Question. I'm working on them. I didn't finish even 10 students. So I was asking somebody else question. I don't think I will be able to finish them anytime soon. Maybe it will make 2-3 weeks, maybe after spring break. I know you have drop date, but if you really think about drop, just talk to me in the office hours or just send me a Piazza message if anybody want to drop. So far among I think 9 students I finished, they got added like 20 to 30 points extra to their grade. It was very, very decent addition. Will the remaining students will be the same? I don't know, but so far out of 9 students, that's what I added. Okay, I cannot release these 9 students yet. I want to finish everybody and then I can release them. Yes. We'll have a new material on Monday. Yes. That's what you want. So what kind of review session you want?
I don't know.
Yeah. Oh, that's very clever. At the same time, you think so little of me. Okay. Uh, I mean, my review will be just basically, I will just bring up previous lectures and just talk about stuff that I think may matter.
Yeah.
But that will be a lot of slides. What? Yeah, I will not do that.
Said this test won't require any type of Python code, but I don't think I've done a single college quantity homework that we did. I'm trying to figure out what kind of questions you're gonna ask.
I'm trying to make the matrices, even homework one, exam one, actually, exam one, you could have done it without Python.
Old exam.
Yes.
Oh, I got maybe Python.
Yeah, I mean, if, yeah, you can use the calculator. Right? Yeah. You could, yeah. And somebody was asking, yeah, so I don't think you will need, I will know later this week, but I don't think you will need a Python. I try to make sure you don't need a Python, but it's up to you if you want to use it. So it's up to you if you want to use it. Somebody was asking Piazza that their laptop battery doesn't really work. So we have these things in here, but also the library, actually, our library, you can go and borrow basically a laptop, and you can just walk in, borrow the laptop and get out. So you don't have to make a, there are some, like if you look for a DSLR camera and some other item like iPads, then you have to submit 48 hours beforehand. But for a laptop, it's just a walk in. You just walk in there, get the laptop the day before, and just set it up for whatever you like, and then just bring it here. That would be my solution. Or just bring extension code. Yeah, yes, Mia. No, they don't. I have been teaching distance learning students since 2005, I think, or 6, and by far they are the most responsible, most clever ones. And actually, I have this student who's actually in this class. He's working with one very awesome organization in Texas, and I love to look at his solutions. Let's put it that way. They are some other level. So it may sound like as it's not fair, but they are very mature. They are very responsible, and then through GTPE they have a mechanism where they have to sign certain things not to be obligated. So usually what they have a and this is not something I do. This is GTPE in charge of it. They have somebody in their company or their team who's kind of their their instructor. So they go there, they look at the setup, they take the exam, and then they sign some form to say, okay, I was there. All what they have access is this following, and then they didn't really cheat or talk to anybody. So they have those people there in their company. They call them coordinator or something like that. But GTPE in charge of that, so they identify those people. But you will be surprised basically by the quality we get through distance learning students. It's not all of them, but it's very impressive for some of them. And the three we have, I think, all three mature. I talked to them, but one of them I really enjoy looking at their solution from a previous class as well. Yeah. Everything, including today's. Another question? Yes. Oh, sorry.
Python, and then but still it's like the calculation that obviously doing it and copy it to very handy. The second is also a lot of calculation.
I won't say a lot, but no, it's simpler calculations. Yes, it will be simpler than just all these segments. Yes. Yeah. Hmm.
We want to know a lot of.
You mean for the homework or for? Okay. Hmm.
So, like she said, will there be a lot of calculating and then bringing it into Canvas?
No, it's a pencil and paper exam.
Oh.
Yeah, it's a pencil. Yes, we're going all days, old school. Yes. Oh yeah, over laptop. Yeah, but you will be here. Yeah. I think it's more fair that way. Pen and pencil. Yes.
On average, under 30 points, do a good job. They're like,
It will not be fair to those who really solve the problem really, really nicely.
those people get the unsolvable problem.
Was that?
Those people get the unsolvable problem. Some people actually couldn't solve the variable.
Some could not. Yes, yeah, for sure. Some could not solve it, but there are people who really made an assumption and moved on, and I really enjoyed that what they did. And that's a very good assumption, actually. So it's a very solid mathematically, and it turned out that they already have a math major. Yeah. Yeah, the pseudo inverse, right? The pseudo inverse. Yeah, they did the pseudo inverse. They didn't get the exact answer, but I could easily see how they got. Yeah. They did the pseudo inverse. I think there are 3 or 4 who did that. So for those, definitely, I want to make sure that we treat them fairly because they really made the extra effort. Okay, we'll see you Monday. Thank you.